Welcome back. This is an Aleks homework video on calculating the solubility of an ionic compound when a complex may form. Okay, so if you have an ionic salt, okay, sodium chloride, and something like that's going to be very soluble. But there's other things that are not soluble. They would have a very, very, very low solubility. So it would just float on top of the water if you were to try to dissolve it. And even if you have something that dissolves a tiny bit, you could determine how much it dissolves. But when you have a complex, okay, something that is not actually an ionic compound, but almost a metal being kind of fixed inside a chemical, that can do all kinds of things to the solubility. Sometimes it can actually increase the solubility, but what it does is it monkeys with what you think of it as being soluble or insoluble. Okay, so let's look at this first example. They've got silver chloride, and silver on its own is chlorine on its own would dissolve very well, usually. Most chlorides will dissolve in water. Silver is one of those weird ones that doesn't really dissolve. It's kind of an exception to the solubility rule. And so you would really just look this up in Aleks. And so when I did, I first of all wrote its solubility expression. I just wrote a reaction. You have silver chloride solid, which is breaking apart into silver ion and chloride ion. Both of those are aqueous. And if you wanted to, now remember that silver chloride is solid, so you would ignore that when you do a solubility equation, but it's simply going to be KSP, which is your solubility product. It's simply equal to the product of the concentration of the two ions present. So I looked that up and found the solubility product there is 1.77 times 10 to the negative 10, which is really, really small. It's not very much at all. Then it was a little hard because I can't solve for two different unknowns at once. So I just realized that it's AgCl, and for every Ag I'm going to have one Cl. So they're equal to each other. So I just set it as x squared, and then took the square root of both sides and got 1.3304, and then took it to two significant digits. So the first one, solubility in pure water, really is easy. You simply look up the solubility product in the data table, and then in this easy example, I simply square rooted it. So my next question is, if I were to break Ag and Cl up, okay, and I've added a salt to that, sodium cyanide. Sodium cyanide is a salt, so sodium ion is going to come out, and cyanide ion is going to come out. My question is, do any of these form a complex with silver? Okay, so the only other possibility would be sodium and chlorine, and it's just table salt, and it dissolves perfectly in water. So does the formation of a complex, is it possible? So I simply go to the data table in Aleks and look for silver making a complex with cyanide. So there's a complex formation table. Look it up, and I found that yes, there was, that you can make AgCN subscript 2. Okay, so that is, and the whole thing is acting as an anion. So that means I need two cyanide ions in order to make this, and the whole thing ends up negative. So I've written out my new reaction. Ag plus 2 CNs give you this complex. And there is a complex, a K sub F, or a formation constant. That is from the Aleks data table also. So here is my new expression, the silver complex divided by silver ion also divided by the molarity of the chlorine ion. All right, so you've got two different things going on because you still have water there, because really it was just salt dissolved in the water. So you have the same thing going on that we already saw in the first example, where silver chloride is dissolving in the water. So we have a case of SP, and we have a case of F also. So that makes this a headache of a problem, because you actually have to deal with two constants at the same time. So I'm going to add them together. So I'm going to look and see that I've got silver on both sides. Okay, so I can strike the silver from both sides and then add them together. Okay, so you're going to add the left to the left, then have the arrows, and the right to the right, and then write everything down. The case of SP and the case of F don't add together. When you combine constants, equilibrium constants, you multiply them. Okay, so just keep that in mind, or you will miss this. So you add the two together, just like you've done to lots of stoichiometry problems, but you multiply the constants. Okay, so here is the new expression. You've got your silver complex times the chlorine ion divided by the square of the cyanide ion equals the product of KSP and KF. So, did an ice table. Okay, nice easy ice table. Nothing's produced, nothing's produced. The cyanide we already saw we had, and so we're just going to put that in the expression that we just had, the green over here on the side. So I hate quadratics and I hate squares and all of that, but this is actually easy because I've got an x square on top and I've got the bottom also squared, so the whole thing is a perfect square. So I just take the square root of both sides and then take it down to two significant digits, and I get it as x equals 0.20 molar. And so look what happens. Do you see that when you add something that can make a complex to the soup, you can increase the solubility sometimes terrifically. And in this case, you've gone up from, to the -5 to the -1. So, 10,000 times. That's pretty good. So I hope this helps you.